There we go. All right, good morning, guys. um, so I am finishing up the exams. I know I promised you I'd have them done on Monday. It's just taking considerably longer than I thought. I had a few people just take the exam in the last couple of days, but I've got just a little tiny bit more to do, and then everything will be done. So I promise you those grades, they'll be in very, very soon. And we'll talk about any sort of grade adjustment that needs to take place after I've been able to run the stats. So I owe you an apology. I am sorry. Things have been a little wild on my end. But today we're going to continue talking about sequences. I appreciate the understanding. So exam 1 scores coming soon. Okay. I don't like to go through, so I could grade these things quicker if I went through and just did person one's test and then go to person 2 and then to person 3. But in order to avoid any potential biases that can come up with that, I go through one question at a time. And because of the way these things are, I've got to print them and then arrange them and flip through looking for stuff. I'll talk a little bit more about formatting and how we might be able to speed this process up for exam 2 so you don't have to wait too long before exam 2. But for right now, exam 1 scores, they are coming, I assure you, we're very, very close. Today, our sequences. So we talked about sequences last time. We looked at the graphs of some sequences. We even defined a few special kinds of sequences. Today I want to talk about a couple more special kinds of sequences, and also give you some practice taking limits and review some of the theorems and rules that we're going to need. So we're going to talk about limits, L'Hopital's rule, and some theorems, and also a couple special sequences. So like the Fibonacci sequence was a special sequence that we talked about last time. But for the purposes of calculus and what we're doing, the Fibonacci sequence isn't really a big deal. It's neat and it does have a lot of nice mathematical properties, but we're trying to talk more about convergence and what it means for a sequence to converge. And since the Fibonacci sequence is a sequence that just gets bigger and bigger and bigger and bigger, it's not really one that's of interest to us. The most important definition from last time is that a sequence is said to converge. Let's say a sequence AN is said to converge if the limit as n goes to infinity of AN exists and is finite. So this is our second notion of convergence. We know what it means for an improper integral to converge. Now we know what it means for a sequence to converge, and they're totally different. There are some similarities in the sense that this is an infinite process, and if it ends with a finite result, then we say that the object in question is convergent or converges. And that's what we had for improper integrals also, right? It was an infinite process, we're integrating over this huge range. And then if we got a finite answer out, we said the integral converges. So that's kind of the similarity there. That's why we study these things one after the other, is because the word converge, although they mean different specifics, generally mean the same thing. Infinite process, finite result. Of course, if a sequence fails to converge, and that could mean a couple things, either the limit is not finite or doesn't exist, either one, then we say the sequence AN diverges. Okay? So that's what it means for a sequence to converge or diverge. Examples. The sequence AN equals, last time we looked at 1 over n. The sequence n squared. His terms just reminding you of notation. Oh, I'm sorry, I might have to take this. Hello? Hello? Fuck. So A1 is 1. A2 here is 2 squared is 4. A3 would be 3 squared is 9. A4 would be 4 squared is 16, and so on. These are the first few terms of that sequence. This is divergent. Because the limit as n goes to infinity of an is the limit as n goes to infinity of n squared is infinity squared, which is infinity. So here the limit is not finite, therefore the sequence is divergent. I want you to be very careful with your notation. All right, no bullshit, no slop. You gotta write stuff exactly like this. You gotta write the limit n to infinity in front of anything you're taking a limit of. Be very careful about not putting equal signs between things that aren't equal. As we move from 11.1 on sequences into 11.2 on series, the notation is going to be so important that even tiny little slips in notation can be catastrophic. So I want you to be very, very disciplined with how you're writing things and how you're using words. It matters more in this part of this class than anywhere else in the entire calculus sequence. So n squared is divergent. No real surprises there. Let's look at a convergent sequence. So let's determine whether the sequence an equals 2n plus 1 over n minus, or let's say n plus 1, converges or diverges. So what it means for a sequence to converge is that the limit exists and is finite. No, Dalton asks, do we have to write infinity squared? No, you could just write infinity. Oh shit, I'm sorry, I am expecting an important phone call. Hello. Oh, Beneful grain-free with chicken. So if you look in the dog food, they do have it at Walmart, but if you don't see it there, just grab any other grain-free food. His tummy is a little sensitive. They have it, it's usually like on the back right, in the dog food aisle. Okay, cool. Everything going okay? All right. Oh, you're sweet. You don't have to do that, but yeah, just be careful. All right, I love you. Sorry. My wife doesn't have a driver's license yet, but she never needed one, but she took my car this morning, so I am definitely a little nervous. Anyway, we want to know whether this sequence converges or diverges, which means we need to calculate the limit as n goes to infinity of an. Sometimes you just got to let shit go. All right. So this is the thing we need to calculate. If this limit comes out finite, then the sequence converges. If this limit does not exist or comes out infinite, then the sequence diverges. This is the limit as n goes to infinity of 2n plus 1 over n plus 1. And as n goes to infinity, this looks like, well, the top is going to infinity and the bottom is going to infinity, which is an indeterminate form. And we're going to have a full discussion on indeterminate forms in a little bit, but I just want to point out that the top and bottom are both going to infinity. L'Hopital's rule could help you here, but what I want to do, one of the things I want to do is to start, I want to make you allergic to L'Hopital's rule. I want you to not like L'Hopital's rule as much as you do. I'm assuming that you like L'Hopital's rule a little bit, but I want to get a little bit more comfortable attacking these things algebraically. So while we could use L'Hopital's rule here, we don't necessarily need to. I appreciate that, that's sweet. So this is an indeterminate form. Infinity over infinity could come out to anything. And because it's not a real number, because it's just an indeterminate form, you'll often see me put these in quote bunnies, like I'm not responsible for this shit. But that is an indication that we could use L'Hopital's rule here if we wanted to. However, a more clever approach is to ask, well, why is the top going to infinity? Why is the bottom going to infinity? That's because the dominant term here, 2n, and the dominant term down here, n, both get big. So if I divide out top and bottom by n, I will kind of renormalize. And the physicists love doing this stuff, renormalization. I can renormalize this guy into something that's a little bit easier to work with. So I'm going to multiply top and bottom by 1 over n, or divide top and bottom by n. And in general, what you want to do is divide top and bottom by whatever the fastest growing term is that appears anywhere. Now I distribute, and I get lim n to infinity. 2n times 1 over n is 2, plus 1 times 1 over n is 1 over n. And downstairs here I get 1 plus 1 over n. And as n goes to infinity, 1 over n goes to 0. So this is 2 plus 0 divided by 1 plus 0, which is 2. So the sequence an equals 2n plus 1 over n plus 1 converges to 2. And this trick works really well for most algebraically defined sequences. Definitely any rational sequence where the top and bottom are both polynomials in n, this will work great. In fact, it might look familiar. This is something that you often do in pre-calculus when you talk about horizontal asymptotes, in Calc 1 when you talk about limits at infinity. But I think it's sometimes treated a little bit less rigorously. It is. It's very much like finding horizontal asymptotes. And this, this leads us to our first theorem, in fact. If an is equal to f of n for some function f of x, then lim n to infinity an is equal to lim x to infinity f of x. And this is the horizontal asymptote for f of x on the right. So as I've been grading the exams, one thing that I find myself writing a lot is, you know, you need to know these basic graphs, right? The graphs of logs and exponentials, polynomials, rational functions. It's true that L'Hopital's rule could do this, but L'Hopital's rule is a little bit clunky, and we want to kind of get away from L'Hopital's rule and get towards some stuff that works in more situations. I see some other questions in chat here. Where did the 1 over n come from? So I decided to divide top and bottom by n because the dominant term upstairs and downstairs is n. So the trick that I'm introducing here, you divide top and bottom by the fastest growing term. This is one way to handle indeterminate forms like infinity over infinity. It's a way to avoid L'Hopital's rule. And that's something that I want to start training you on, is how to avoid L'Hopital's rule. The big issue with L'Hopital's rule here is that this is a sequence. It's not a continuous function. So the idea of taking a derivative of 2n plus 1 doesn't make sense. Remember, the graphs are just dots here. So we can't really talk about all of the limit and derivative stuff that we would like to talk about unless you relate it to a continuous function. And that's what our theorem does. So before we can even consider applying L'Hopital's rule, we need something that we can differentiate. You can't differentiate a collection of dots, you differentiate curves. This sequence is just a collection of dots. So I couldn't really talk about the derivative top or bottom, but what I could do is relate it to a continuous function and then apply L'Hopital's rule to that if we wanted to. But this is a way to avoid that shit altogether. So what I'm trying to teach you here is what's called rigor, mathematical rigor. Strictly speaking, there is no such thing as the derivative of a sequence. Can't do it. Sequence, I mean, you have to be continuous to be differentiable. A sequence is not at all continuous. It's just a bunch of little dots. So the notion of the derivative of a sequence isn't really a valid one. And in order to even approach that, you would have to use this theorem. And my point is that if you don't want to have to lean on this theorem, then you can do this stuff instead. This theorem is necessary for L'Hopital's rule. And then L'Hopital's rule is itself a little bit clunky. So why bother with that when you could do this? It's very, very quick. So we have a few other questions in chat. Dalton points out that via L'Hopital's rule, you could see very quickly that it's 2. That's correct. But L'Hopital's rule, strictly speaking, doesn't apply to sequences without this theorem. Simon asks, can we do this to terms that are under a square root? Yep, you absolutely can. I'll show you some examples like that. And then Fernando asks, what's the name of this method? And would I take points if you use L'Hopital's rule on a sequence? If you use L'Hopital's rule on a sequence, I want you to go through this theorem first. So I'll show you what that looks like in just a second. I would not take points off if you use L'Hopital's rule, unless a problem explicitly said, don't use L'Hopital's rule. There will be problems where L'Hopital's rule is necessary. But there are problems where L'Hopital's rule can be tempting and is not the right way to go because either it takes longer or for whatever reason you can't apply this theorem. So let's solve that same problem using L'Hopital's rule. I could say an, which is 2n plus 1 over n plus 1, is equal to f of n, where f of x is 2x plus 1 over x plus 1. Therefore, by our theorem, the limit as n goes to infinity of 2n plus 1 over n plus 1 equals limit x goes to infinity 2x plus 1 over x plus 1. And here I could apply L'Hopital's rule, right? You cannot differentiate n's. That's the basic idea here. N's or sequences don't have derivatives because you can't talk about getting close. You can't talk about limits anywhere except at infinity, which automatically means you can't talk about the derivative because the derivative is defined through a limit, not at infinity, but at like a 0, right? And I can't talk about getting close to 0 in terms of a sequence because either you're at 0 or you're not. There is no nearby because the graph is not a curve, it's just some dots. But now if I apply L'Hopital's rule to this function rather than this sequence, I will get the result. I get lim x to infinity, derivative of the top is 2, derivative of the bottom is 1, so you're taking the limit as x goes to infinity of the constant function 2. But you have to lean on that theorem. You have to relate your sequence to a function of a continuous variable, and then and only then can you apply L'Hopital's rule. Okay. So the issue there is a subtle one, but it's important to take note of. The only calculus operation that is valid with sequences is a limit at infinity. I can't take a limit anywhere else, which means I can't really talk about derivatives, which rules L'Hopital's rule out. Now, Simon asked a good question. Can we do this sort of stuff under square roots? I would like to show you an example like that, but I also want to talk about a couple other theorems. Let's see. So that's the theorem we just covered. Those are those definitions. We've talked about those. I just want to make sure I'm not skipping anything. Okay, yeah, two other theorems. Before we address that, let's look at an example along the lines of what Simon was asking. Okay, so the same sort of thing. Let's investigate the convergence. Of the sequence an equals n over the square root of 2n squared plus n. So the if I try to take the limit right away, of course, that's the limit as n goes to infinity of n over square root 2n squared plus n. The top goes to infinity. The bottom looks like the square root of infinity, which is infinity. So this is indeterminate. This is a good example of a problem where you really wouldn't want to jump in with L'Hopital's rule. The derivative of the bottom is kind of messy. It involves the chain rule, and it's going to be kind of unpleasant. However, the fastest growing term upstairs is n. The fastest growing term downstairs is the 2n squared, but it's under a square root. So that's like growing at the speed of n. So if I divide top and bottom by n, I just call it the divide top and bottom trick. Fernando asked, what's the name? I just divide top and bottom by the fastest growing term. I guess I've never really given it a particular name. You can call it renormalization if you wanted to. I think that's a term from physics that is sometimes used for things like this. So if I renormalize this sequence by dividing top and bottom by n, I'll get limit n to infinity, n times 1 over n divided by the square root of 2n squared plus n times 1 over n. And now Simon was asking, how do you do this when there are square roots involved? And the answer is, downstairs, you need to get the 1 over n to interact with the 2n squared inside here. The only way to do that is to write the 1 over n as the square root of something, right? Because you can multiply two square roots and then just rewrite that as one square root with the product inside. So I'm going to, upstairs, I'll just cancel those. N times 1 over n, that's 1. And downstairs here, I'm going to rewrite this as the square root of 2n squared plus n times the square root of 1 over n squared. Right, 1 over n and the square root of 1 over n squared, those are the same as long as n is positive. And now that I've written the bottom as square root times square root, I can smash them together. So I get 1 over, and now I've got a single square root, and inside is 2n squared plus n times 1 over n squared. And then I distribute. 2n squared times 1 over n squared is 2. And n times 1 over n squared is 1 over n. Of course, as n goes to infinity, 1 over n goes to 0. So this limit is 1 over the square root of 2, aka root 2 over 2. I really can't be answering the phone so much, sweetie. Oh no, what is this bullshit? Hello?
This is an important message regarding your current credit card account. Before we are unable to lower your credit card interest rate, this is your final courtesy call. We have made several attempts to reach you. Press 9 to speak with the member service department, or press 2, and your eligibility will expire today.
All right, I'm curious. I've gotten this spam call like 5 times.
Right away. Please hold the line for the next
I know, right?
representative.
I'm just curious.
Hi, how are you?
Hello.
Yes, how are you doing today?
I'm doing great. How are you?
Yeah, same.
That's good. So I'm actually a professor of mathematics, and you assholes have called me like 4 times in the last hour. Who are you with? What company do you work for? Lol. All right. Hopefully they won't call back again. I wish, man. I wish. Justice would be me calling them while they're busy. But one day. All right. So let's come back to our theorems. This divide top and bottom trick or renormalization trick is really good. If for whatever reason you don't like this trick or you're working on a problem where you think L'Hopital's rule would be faster, just remember to use your theorem. And remember to relate the sequence to the continuous variable function first. There are some other tricks that are good to know when it comes to dealing with limits of sequences. So I've got 2 more theorems I want to show you. This says if f of x is a continuous function, and the limit as n goes to infinity of the sequence an is L, then the limit as n goes to infinity of the new sequence f of an will be equal to f of the limit as n goes to infinity of that sequence, which is f of L. So this is actually a characterization of continuous functions. Yeah, stay out of the hospital. Avoid L'Hopital's rule, if you can. And then down here, you can shove limits inside and out of continuous functions. This is something that we talk about in Calc 1, but not in the setting of sequences. So sometimes this can be super useful. Sometimes the only way to attack a problem is with that. Another theorem I want to give you before we go back to working examples. I guess there's really 2 more. The limit as n goes to infinity of a sequence an is equal to 0 if and only if the limit as n goes to infinity of the absolute value of an is 0. So sometimes if you think a sequence might be tending to 0, but you're having a hard time showing that, you can work with the absolute value of that sequence instead. If you're able to show that the absolute value of that sequence goes to 0, you can conclude through this theorem that the sequence itself goes to 0. And then the last kind of useful theorem here is the squeeze theorem. But in the particular setting of sequences. So this says if an is less than or equal to bn is less than or equal to cn are all sequences, and the limit as n goes to infinity of the outer guys, an and cn, match, say they are both L, then the limit of the bn's is also L. Okay, so these three theorems, super duper useful for computing limits of sequences. These, together with the earlier theorem and L'Hopital's rule, then we've got, if you don't state the theorem and use L'Hopital's rule, you're going to L'Hopital. Yeah, I think we could even, Dalton, omit the the there. I think the capital L in L'Hopital would be French for the. But funny story about L'Hopital's rule. I don't know if you guys have heard this story before. I don't want to waste too much time. This guy is an asshole. L'Hopital, not a cool guy. He stole that theorem. It was not his. He didn't come up with it. He didn't prove it. He actually paid somebody for it. One of the Bernoulli brothers, this Jacob and John Bernoulli from the same time in continental Europe. And L'Hopital straight up stole the theorem from them. He paid them for the rights to publish the theorem in his own book. So lots of reasons to hate L'Hopital's rule, right? Now I do have two other theorems on sequences, but they're not useful for computation in the same way that these four are. So I'd like to spend a minute playing with these before we talk about the other ones. The other ones are a little bit more abstract, and they're more about establishing the existence of a limit than actually calculating it. So a good fun toy example for this is or investigate the convergence. Let's say it like that. Of the sequence an equals -1 to the n over n. Right? So I can look at the first few terms. It's never a bad idea to do that. A1 here is -1 over 1 is -1. A2 here is -1 squared over 2, that's +1/2. A3 is -1 cubed over 3, that's -1/3. A4 is -1 to the 4 over 4, that's +1/4, and so on. We can look at the graph. Also never a bad idea. I'll mark this as +1 and this as -1. And we'll go 1, 2, 3, 4, 5. A1 was -1, so we start off way down here. A2 is +1/2, so that's like right here. A3 is -1/3, so that's like right here. A4 is +1/4. A5 would be like -1/5. And as we go further and further out to the right, these dots do appear to be getting closer and closer to something. My next term would be like here and then like here. It looks to me like these are getting closer and closer to 0. But if you try and just jump in and take the limit of -1 to the n over n, you get -1 to the infinity over infinity, which is like dne over infinity. We saw that the -1 to the n sequence is divergent last time, remember? That was one of our examples of a divergent sequence on Monday. And you might think that dne over infinity is dne, but you'd be wrong. We just don't know. So this is inconclusive. I don't know what's going on with that. But I have a theorem. It says lim n to infinity an equals 0 if and only if lim n to infinity absolute an equals 0. So how do you spot when you should use this theorem? Well, you look at the graph or you look at the first few terms and you say, oh, it looks like this sequence is going to 0, but I can't tell via any of the obvious tools. So I suspect that my sequence is going to 0, and in order to figure it out, I'm going to look at the absolute value sequence, because my theorem says if the absolute value sequence goes to 0, so does the original. Here, the limit as n goes to infinity of the absolute value of an is the limit as n goes to infinity of the absolute value of -1 to the n over n. And now absolute values are multiplicative, meaning you can split them up over multiplication and division. So this is lim n to infinity, absolute value -1 to the n over absolute value of n. Since I'm sending n to positive infinity, the absolute value of n is just n. And up here, the absolute value of -1 to the n is the same as the absolute value of -1 to the n like this. The power can commute out of the absolute value. So these are some algebraic properties of absolute value. Split up nicely over multiplication and division. Powers commute, meaning powers can come in or out of absolute values without causing trouble. The absolute value of -1 is 1. So you get lim n to infinity, 1 to the n over n. 1 to the n is just 1. So this is lim n to infinity, 1 over n, which we know is 0. So the absolute value of an has limit 0. Therefore, by our theorem, an itself has to be 0 also. In other words, or that is, the sequence an equals -1 to the n over n converges to 0. So that's one application of that one theorem, the theorem on absolute values. Yeah, I like it. It's nice. Getting comfy with absolute values is something you're going to need to do. There's some algebra that is a little bit unique to this section of the textbook, and the algebra of absolute values is among those things. So maybe I should show you some of the properties of absolute value really quickly. First though, no, this is a fine place to do it. We're just using it now, so I'll do the other example after this. So some properties of absolute value. The absolute value of a times b is the same as the absolute value of a times the absolute value of b. This is what's called a multiplicative function. The absolute value of a ratio, a over b, that's the same as the absolute value of a over the absolute value of b. And the absolute value of a to the b is equal to the absolute value of a raised to the b. So these three properties of absolute value, we'll use these all the time. There's one more really important one called the triangle inequality, and we'll use this once or twice, but very rarely. We will use this when we get into section 11.6. It says that if you add two numbers and then take the absolute value, that's never larger than what you get if you take the absolute value of the two numbers and add them up separately. Yeah, I'll bring the last page back up. All right, this is most of the important stuff. Simon, are you the one calling my cell phone with credit card offers? It's a scam. It's like a next level scam. I don't mind you guys taking screenshots. In fact, I encourage it. All right, if you're having a hard time like writing everything down, a screenshot's a really good idea. You're also welcome to download the YouTube videos, whatever you want. Okay. Anything else on here that that we need to see? Anything that we missed? Well, so let me zoom in. From here to here, I split up the absolute value. From here to here, I'm using this third property that says the absolute value of a to the b is the absolute value of a, all raised to the b. So the absolute value of -1 to the n is the same as the absolute value of -1 raised to the power n. How'd it go? And then finally from here to here, the absolute value of -1 is just 1. So the absolute value of -1 to the n is 1 to the n. And here to here, the exponent goes away because no matter what you plug in for n, 1 to the n is always 1. So this last step where the exponent of n vanishes is just an identity. 1 to the n is always 1. Okay. So I am going to pull this page to the side. I do encourage you to write these properties of absolute values in your notes. We're going to use them a lot. -1 to the infinity. Yeah, you can say -1 to the infinity is always dne. Remember the graph -1 to the n just bounces back and forth between 1 and -1. This graph looks like this. So these points are definitely not getting closer and closer to anything as we go off to the right. So the limit as n goes to infinity of -1 to the n, that's really the careful way to write it. This does not exist. So I haven't given you the rigorous definition of a limit for a sequence, right? The delta epsilon definition. But the idea is the same as it was in Calc 1. If as n gets bigger and bigger and bigger, an gets closer and closer and closer to some particular number, that's what it means for that limit to be equal to that number. And here, these guys are definitely not getting closer and closer and closer to any number. Okay, a couple more things here. Where did there it is. So I wanted to show you an example using our other theorem, our theorem on continuous functions. So we're going to investigate the convergence of the sequence an is the sine of pi over n. This is another one of those cases where if you just write the limit out front, it's not immediately obvious what to do. You could write down the first few terms, but they won't really help. I know that what I need to find is the limit as n goes to infinity of the sine of pi over n. And the trick to doing this is just to shove the limit inside the function. Sine is a continuous function, so that limit can be shoved in. So this is the sine of the limit as n goes to infinity of pi over n. And then within the sine function, that pi can pop out of the limit. So I'll have the sine of pi times lim n to infinity 1 over n, like this. And of course, this limit right here is 0. So this is equal to the sine of pi times 0, which is the sine of 0, which is 0. So you can shove limits into and pull limits out of continuous functions. And sometimes that's the only trick that will do the job. Sometimes there's no other way to attack a problem. Any questions on this one? I think this example is maybe a little bit easier to work with than the last. Anything that we're wondering about notation-wise or rule-wise? Yeah, I like it too. So we make use of the theorem right here. Right, it's that equality where we make use of the theorem. It says we can shove the limit into the continuous function sign. And then from there, it's nice and straightforward. Okay, so before I talk about the other theorems on sequences, they're called bounded monotone sequences. We're going to look at, we have a theorem on bounded monotone sequences. I want to introduce you to a special family of sequences. And if you took pre-calc with me, then this will be familiar, but depending on how thorough your pre-calc class was in the sequence treatment, you may not have seen these before. So usually in pre-calculus, we study two special kinds of sequences. Only one of them is really interesting to us here. So in pre-calc, usually you study arithmetic and geometric sequences. I want to talk a little bit about geometric sequences. The basic idea is that so a geometric sequence is the sequence version of an exponential function. That's the easiest way to think of it. The strict definition, if a sequence AN can be written in the form AN equals some constant, which I'll call A0 times R to the N, then we call AN a geometric sequence. So compare this to like C times B to the X or C times A to the X. Same sort of idea, same definition really as an exponential function. The reason we call these geometric is because you can think of these as being like sequences of areas. In fact, if you look at our Canvas page for this class, there is a little image up here. Where is that? Oh, maybe it's not showing up there. I thought I did. Maybe I didn't show it to you guys. So, well, I'll go over the reason why they're called geometric a little bit later. Let's get a feel for them and let's finish the definition. The number R is called the common ratio. So an example, AN equals 2 times 1/3 to the N. This is a geometric sequence. Here, A0 is 2 times 1/3 to the 0 is 2. And that's why I label this constant A0, because it is the output for the sequence when you plug in n equals 0. A1 is 2 times 1/3 to the 1, which is 2/3. A2 is 2 times 1/3 squared, which is 2/9. A3 is 2 times 1/3 cubed, which is 2/27. And you could keep going if you wanted to. one characterization of geometric sequences is that to go from one term to the next term, you're always multiplying by a fixed constant. So to go from 2 to 2/3, to go from the term with n equals 0 to the term with n equals 1, we multiply by 1/3. To go from 2/3 to 2/9, we're multiplying by 1/3 again. To go from 2/9 to 2/27, we're multiplying by 1/3 again. Another way to say that is if you divided any two consecutive terms, like A3 divided by A2 would be equal to 1/3. So the ratio of any two consecutive terms is common. And that's why we call this number R the common ratio. Okay. So a neat fact about geometric sequences is they will converge if and only if the absolute value of R is less than 1. That might be familiar from when you learned about exponential functions, that they'll have a horizontal asymptote on the right-hand side from your perspective like this, if and only if the base is smaller than 1. So one last little theorem here on geometric sequences. A geometric sequence an equals a0 times r to the n will converge provided the absolute value of r is less than 1. I should say converge to 0. Right? So if you take a number whose absolute value is smaller than 1 and you multiply it by itself over and over and over again, those numbers will get smaller and smaller and smaller. If r is exactly equal to 1, then the sequence is actually a constant sequence. So in that case, the sequence also converges. Because it's a constant sequence, it's not doing anything special, it just converges to whatever that constant value is. And then if r equals -1, or the absolute value of r is greater than 1, the sequence diverges. So this is the full result on geometric sequences. And it's not too hard to sort out a proof. The interesting part is that these sequences will converge to 0 if the common ratio is less than 1. That's crucial. And you need to remember all of this. But the only machinery here that we would actually want to get into the workings of if we wanted to prove this theorem would be this part. And the reason that is true is precisely what I said earlier, that if you take a number between -1 and 1 and you start multiplying it by itself over and over again, it will always get smaller. It'll continue getting smaller, and so in the limit, you'll get 0. For example, the sequence that we were just playing with, 2 times 1/3 to the n, 2 times 1/3 to the n. We could say the limit as n goes to infinity of an is the limit as n goes to infinity of 2 times 1/3 to the n. The 2 piece is constant, but the 1/3 to the n piece is going to go to 0. Because if you multiply 1/3 by itself again and again and again and again, another way to think of this is that it's 1 over 3 to the n. 3 to the n goes to infinity, so this is 2 times 1 over infinity, which is 2 times 0. Not every geometric sequence has a common ratio where the numerator is 1, so this trick doesn't always work. The way I would encourage you to think about it is that 1/3 to the n goes to 0 as n goes to infinity, since the absolute value of 1/3 is less than 1. Okay. So I don't think I have a whole lot more that I want to really bust you guys on for sequences here right now. I'd love to start talking about series, but I need you to get comfy with sequences first. I suppose I can show you those last couple theorems on monotone bounded sequences, and then look at 1 or 2 examples. Yeah, so I'll go ahead and relay this this last little bit of theoretical stuff from 11.1, and we'll call it a day there. A sequence AN is called bounded if there is some number, call it capital M, such that the absolute value of AN is always less than or equal to M for all integers N. And a sequence AN is called monotone if it is either always increasing or always decreasing. And then we have the following theorem. Bounded monotone sequences all converge. So I mentioned that this last little bit here is not really useful for calculation. You notice this theorem doesn't say anything about how to find the limit. It just tells you that if you have a sequence which is both bounded and monotone, it is a convergent sequence. In practice, the way we use this is for recursive sequences. If I have a recursive sequence that through some channel I'm able to figure out is both bounded and monotone, then I can assume that the sequence converges. And then that allows me to take limits everywhere in the recursion relation and try to solve an equation for the limit of the sequence. So I'll leave this bit up here for a moment. I want to try and convince you that the theorem is true before I do anything with it. Let me zoom out a little bit. So why would this be true? Well, let me imagine that I have a monotone increasing and bounded above. And let's look at the graph. I'll put M up here. This is my upper bound. I know the sequence AN is never allowed to come above that line. Bounded doesn't necessarily mean the same as not divergent. So a bounded sequence can still be divergent. For example, -1 to the n, that sequence that just bounces back and forth between 1 and -1, that's a divergent sequence, but it's also definitely bounded. It never gets larger than 1. So bounded means does not run off to infinity. Bounded means that there's a line above which the graph of the sequence never goes, which isn't on its own enough to guarantee convergence, because you could have something oscillate like -1 to the n. But if you're bounded above and also monotone, that is enough to force convergence. And that's exactly the point of this theorem. So maybe A1 starts off down here. Since AN is monotone increasing, A2 has to be above him. Since AN is monotone increasing, A3 has to be above A2. And similarly, A4 has to be above A3. A5 has to be above A4. A6 has to be above A5. Can you see what's happening here? No matter what you try to do with these dots, since each one has to be higher than the last one, but none of them can go above this line, they all have to start clustering up on this line. So the sequence has to converge. These dots have to all start getting closer and closer and closer to whatever this least upper bound is. If you have a monotone decreasing sequence that's bounded below, the picture is the same, you just flip it over. Each term has to be getting smaller and smaller, but it can't go through the floor, so the terms have to all start piling up on the floor. Here, each term has to get higher and higher, but they can't go through the ceiling, so they all have to start piling up on the ceiling. Like I said, we don't use this to solve a lot of problems, but there are some, usually recursive sequences. We can try to find limits of recursive sequences. So I'm going to finish today with this example. Let's investigate the convergence of the recursive sequence defined by A1 is equal to 2 and AN plus 1 is equal to the square root of 2 times AN. Actually, let me change this A1 to be 1. Simpler initial condition. And I'll say here we can assume that the sequence AN is increasing and bounded above. So because the sequence is increasing and bounded above, I know it is convergent. I can look at the first few terms of the sequence. A1 is 1, that was given. A2 should be the square root of 2 times A1, which is the square root of 2. A3 is the square root of 2 times A2, which is the square root of 2 root 2. You can see where this is going. A4 is the square root of 2 times A3, which is the square root of 2 times this thing, like that. A5 would have 4 nested square roots. This is the square root of 2 times A4, which would be the square root of 2 times the square root of 2 times the square root of 2 times the square root of 2, all nested like this. So in one sense, the sequence an, if it has a limit, that limit is kind of the result of infinitely nesting square roots of 2. Yeah, these are popular competition problems at the high school level. Since my sequence is increasing and bounded above by my theorem, I know that an is convergent. In other words, the limit as n goes to infinity of an exists and is finite. Let's call it L. The way that we use this theorem to solve problems is we say, all right, I know now that I can take limits, and I can treat that limit like it's a number because I know that it exists and I know that it is finite. So what I'm going to do is I'm going to come back to my recursion relation here and take limits everywhere. If I do that, then what I get is lim n to infinity an plus 1 equals lim n to infinity square root of 2 times an. On the right-hand side, I know that this is the same as the square root of 2 times the lim as n goes to infinity of an. Here I'm using my theorem on continuous functions, saying I can shove the limit inside the continuous square root function. And I know that the limit as n goes to infinity of an is L. So this is the square root of 2L. On the other hand, an plus 1 is just a horizontally shifted version of an. So if you take the sequence an, you picture its graph, and you shift everything to the left 1 unit, it will still have the same limit. It'll still have the same horizontal asymptote. So this is also L. So we get L equals the square root of 2L. This part tends to be something that people have a little bit of trouble wrapping their head around. So I can come off to the side for a minute and say here, lim n to infinity an plus 1. That's really the same as, as n goes to infinity, n plus 1 goes to infinity. That's a infinity, which is L, because lim n to infinity of regular an is a infinity is L. The way I usually prefer to think of it is an plus 1 is the horizontally shifted version of an. So if an goes to L as you wander off to the right, then an plus 1 will go to L as you wander off to the right. In any case, taking limits everywhere in our recursion relation gives us this, which is an algebraic equation that I can then solve for L. Yeah, exactly. So if I square both sides and subtract the 2L over, I get L squared minus 2L equals 0, which is the same as L times L minus 2 equals 0. So either L equals 0 or L equals 2. Here, A1 was 1. And I was told to assume that the sequence is increasing. So the limit couldn't possibly be 0. I'm starting at 1 and I'm going up. Can't be 0. So it's got to be 2. right? Can't be 0 because we're starting at 1 and we're going up. A fun consequence of this, and it's something that I wrote in chalk on the parking lot in my very first apartment, or in front of my very first apartment here in Gainesville, because I was being silly and mathematically enthusiastic and got into a big fight with one of my engineer neighbors over this, is that if you infinitely nest square roots of 2, if you allow that nesting process to go on and on and on forever, then you get 2 out. It's cool shit. It's really counterintuitive. And one way you can get there is by thinking in terms of recursive sequences and bounded monotone sequences. There won't be a lot of problems like this for you to solve. There will be maybe 1 or 2 in the homework, maybe 1 on a test at some point, but it's not something I'm going to beat you to death with. The main thing that I care about right now in 11.1 is that you're getting comfortable with the notation, and you're being very, very careful with the notation and the terminology. So here I would say, hence the sequence AN converges, oh, thank you, sweetie, to 2. So I want you to be practicing with the limit rules. Avoid L'Hopital's rule as much as you can. You can use it from time to time. And next time we talk, we're going to have an in-depth conversation about indeterminate forms and all the different ways that you can use and must use L'Hopital's rule every now and then. But for the most part, I want you to be trying to use that renormalization trick, use the squeeze theorem, try to make use of the theorems that we have, and try to understand the inputs and outputs of those theorems. So all of those theorems say, if this, then that. I'll have to look. So I think you probably have just about everything you need to do all the homework. There might be 1 or 2 problems in here. Yeah, so number 16, this, unless you're feeling very clever, this does require L'Hopital's rule. And technically you've got everything that you need to do these, all of these. You could finish the whole homework. But if you have trouble with number 16, don't feel bad. This requires a little bit of work. You have to relate this to a continuous function. So replace the n's by x's. Then you have to take natural logs and then use L'Hopital's rule. So this is one that we have not done an example of, even though we've talked about the theory that you need. All the others you can do. Some of these factorial problems you may have a hard time with. But pretty much all of this is just following from the definitions and the rules that we've covered. The only things that you might struggle with are those 2, but I would implore you to actually struggle with them. So 11 and 16 might feel difficult because we haven't done explicit examples like those, but we've covered everything that you need. And I will definitely talk about those, I guess not Friday because we have the holiday, but Monday of next week. And then next week we will begin talking about series. So work hard on this homework. You should be able to get it all done, but if you get stuck on those 2, don't feel bad. We'll talk about problems of that sort on Monday. And then next week, we're going to have a little bit more sequence homework and a lot of series homework. So get ready. The hard part is coming. The hard part is here. The more time you put in now to understanding sequences, the easier series will be. Series are definitely what give this class its reputation. This week's homework is pretty short. So I don't think you'll have a hard time getting through it. And I want you to be careful as you do it. So you shouldn't have to rush. Make sure you're writing all the words, right? Make sure you're writing, the sequence da-da-da-da-da converges to da-da-da-da-da, or the sequence diverges because this. And when you use a theorem, state the theorem, its hypotheses and its conclusions, to try and get really comfortable with this style of logic and thinking. Draw some graphs, right? Drawing graphs is a really good thing to do anytime you're solving any problem, but especially when you're getting to know a new problem type. So as you are getting comfortable with the idea of what a sequence is, drawing the graphs will help you feel a little bit more of the intuition. I think that's a good place to end it for today. So I will stop here. I am going to have my office hour from 1 to 2, and then this afternoon I am going to grind until I finish grading your tests. I'm very close. I think I have one more question that I need to grade for like 3 or 4 people, and then everything will be done and I'll input the scores. Let me show you really quick in these last few seconds how I'm going to input the scores so you don't get confused or frightened. Right now, there are 2 assignments associated with exam 1. There's this guy and this guy. So I'm going to put your scores in here to start, because this already has your points for the true, false, and multiple choice. Once I put the scores for your free response questions in here, the percentage score will be whatever that percentage score is. If we end up doing some curving or some rewrites or any sort of grade corrections, then we'll do that and I'll update them here. And once everything is done, I'm just going to copy paste that score here. Because exam 1 is supposed to be worth 100 points, but with the rubric set up the way it is in Canvas, it would not let me make this assignment worth 100 points. So we're going to do 50 points here, 50 points here. The grade that I enter in both will be the same. I'll just take whatever grade you end up with here and I will copy paste it down here. But before I do the copy paste, I'm going to do any sort of curving or adjustment that is necessary in here. So later today, you're going to see your exam 1 score show up here. That will be the raw percentage score for the test. And if we don't end up doing any curving, that's the exact score that I will paste here, so you get the full 100 points for the test. If we do end up doing any curving or anything like that, I will apply that here before copy pasting here. Question 11 and 16. All right, so I hope that's all nice and clear. If you want to talk about any more problems, come see me in my office hour. That'll start in about 10 minutes. Otherwise, I hope you guys have a wonderful holiday weekend. Please stay safe, be careful. If you have pets, don't let them out on the 4th of July. Any last minute questions for me? Alrighty, this sounds good. Ryan, if you don't mind coming by the office hour, we can talk about those last 2 problems over there. And anybody else wants to talk about any other questions, of course, you can bring those to the office hour as well. Again, have a safe weekend, and I'll see you guys on Monday.